Alright, welcome back, Engineering 270, Lecture 2B. So we want to look at how we take these assembly language instructions and translate them into binary, into machine code. Because we can say something like increment file register hex 20, and that means something to us, but to the actual hardware, the actual PIC processor, these ASCII codes are way too complex for it to know what to do. It needs very simple ones and zeros to be able to perform its decode and execute steps after it's fetched an instruction. So in program memory, we're going to store a series of 16-bit words, each word generally specifying one of these assembly language instructions. So we need to know how to translate from assembly language into binary, into machine code. And to do that, we look at figure 20-1, and we see a template. So here's a description of how we write a byte-oriented instruction like increment f. And I'm going to copy that over onto our notes here. So there's 6 bits of opcode that tells us what we want to do. There's 2 bits we're not going to worry about too much for now. These are called D and A. And then there's 8 bits which specify a file register. So I'm writing those 8 bits as FFFF. That's not a hexadecimal number. Okay, it's actually F0, F1, up through F7. These are 8 bits. Okay, each of these is a 1 or a 0. It's just a convenient way to specify 8 bits that correspond to a file register. Well, what's the opcode for increment file register? Come down to table 20-1 and look up INCF, and you'll see the exact template spelled out over here. So increment F looks like 0010, 10DA, and then 8 bits of file register. Right, I'm just reading this from the table 20-1. So we know the opcode 001010. The destination bit, since we want to write the result back into the file register, D is equal to 1. The access bit we're not going to talk about for a few minutes, but for now we're just going to assume that it's a 1. And then the file register should be the 8 bits corresponding to hex 20, which is 00100000. So the full binary coding for increment file register 20, where you implicitly said destination bit of 1, is the following: 00101011 00100000. That's the 16 bits corresponding to this instruction. And since binary for humans is error prone, we usually write this in hex. This would be a 2, a B, a 2, and a 0. There's the 4 hex digit number corresponding to this opcode and this operand. And if we go in the opposite direction, if we're given a binary instruction and we want to convert it into assembly language, it's just a pattern matching. You go through the possible templates and you try to find a pattern that matches, right? And the first 6 bits, sometimes 7 bits, is hardwired, so you've got to match those exactly. But if you can match that part of it, then you just take the corresponding bits in your binary and say, okay, this is what A is equal to, this is what D, this is what the F is equal to, and you use that to figure out what the assembly language instruction is. So there's some homework questions to go back and forth on that. And it's really important to get good at this process of switching between assembly language and machine language. The reason being, because if you understand how this binary coding works, it'll help you understand what you can and cannot do at the assembly language level. For example, if I tried to increment file register 20 and store the result in file register 21, I'd look at my increment instruction and I'd see there's no way to specify 2 file registers. Right? I can specify 1 file register here, and I can use the destination bit to say I want the result to go into W, or I want to go back in here, but I can't specify a 2nd file register arbitrarily. So this is a process you want to get comfortable with, going back and forth between machine language and assembly language. All right, and we need to talk about data memory a little bit more. So data memory is basically 1 byte wide, so 8 bits, and it's addressed from hex location 00 through hex location FF. So there's 256 locations, 256 general purpose file registers. And this address, this is the 8 bits that we specify in coding up our binary instructions, right? So this is the 8 bits that we put in here to specify an operand. So that all works great, but there's one wrinkle in all of this. Remember I said that on the PIC processor, we use memory mapping to access I/O locations. So for example, here's a register called latch A. And we'll talk about what latch A is in the next lecture. But latch A is related to a piece of hardware. And if we want to access it, we do it by accessing file register F89. Okay, well let's think about that. F89, you'll notice that all these hardware interfaces, this is serial communication, this is a timing subsystem, this is oscillator control, and so on. All of these special function registers begin with an F and are followed by an 8-bit file register, but the 8-bit file register goes from FF down to 80. And that's going to be important. Alright, so how would we access file register F89 in hex? Well, if we write that out in binary, it looks like this. And it looks like we need to use 12 bits to specify this file register. And in our coding of instructions, we only have 8 bits available for a file register. So this is where the access bit comes in. And the access bit has the following specifications. If A equals 1, our file register is exactly what we've been doing. It's our 8 bits that we specified, prepended by 4 zeros. So it really is something in this first 256 locations of our data memory. If our access bit is 0, and we specify a file register less than hex 80, the file register is again the 8-bit address we specified prepended by zeros. Again, no change, we're accessing something up here. But if our access bit is 1, and we specify a register bigger than or equal to hex 80, then the actual file register is the 8-bit register we specify, prepended by 4 ones. So what does this mean? If we want to say increment file register F89, well, our opcode stays the same. Okay, that's our opcode. Our destination bit is still a 1. Our access bit, though, we're going to have to do something with. Our file register, since we can only specify 8 bits, we're just going to specify the last 8 bits. This is going to be hex 8 and hex 9. But our access bit, if we set our access bit equal to, sorry, this is a 0. If we set our access bit equal to 0, since our 8-bit number is bigger than or equal to hex 80, this is going to prepend 4 ones to our address F. And so we're going to actually be specifying location F89. So this instruction 0010, 1010, 1000, 1001, or if we were to write it in binary, this is 2, this is A, this is 8, this is 9, in hex, right? This instruction says increment file register F89. If we made the access bit a 1, this would increment file register 089. So So the access bit, and I'm sorry, this is a 0, not a 1. I made a mistake before. The access bit lets us specify whether these upper 4 bits should be a 0 or a 1. And we can use that to access these special function registers that are at the far end of our data memory. So all of these things over here, we access by setting the access bit to 0, and then setting the file register to whatever the last 8 bits are. Alright, so there's some homework questions that will help you work with that. So next time we're going to talk about how we actually use some of these special function registers to start doing things like input and output to and from the pick processor.